Okay, chemistry kids, we're going to go over another kind of solution stoichiometry problem, just stoichiometry in general. And we're going to get into a little bit of, I guess, what you could call a lab technique question or a lab question. Okay, so this is the type of question that might be asked on the AP exam to test lab skills. Now, really, what it comes down to is just stoichiometry. So, can you take the data given from an experiment done and do the calculations needed? So, obviously, on the AP exam, they can't really test your lab skills. They can only test if you're given certain data. Do you know how to do certain calculations? What conclusions can you make from the lab? So, a few different types of lab questions that could be asked translate basically to stoichiometry questions. And so I want to give you an example problem like that. And so I just want to go through it. So this is really focused on 2-2 and 2-3. So it's stoichiometry, but it's also percent composition, percent by mass. And there is a kind of little bonus question at the end, which is solution stoichiometry. So let's get into this practice problem. Hold on. Okay. All right, so it says a sample of white powdery substance has both sodium chloride and sodium carbonate. So we have this white powder, and we know that it's made up of two different solids, sodium chloride salt and sodium carbonate salt. All right. But there's really no way to distinguish how much of it is sodium chloride versus how much of it is sodium carbonate, okay, just by looking at it. So a student wants to determine what percent by mass of the mixture is sodium carbonate. So he takes 5 grams of the overall mixture. So again, in this 5 grams, you have sodium carbonate and you have sodium chloride, and your goal is to figure out what percentage of that 5 grams is sodium carbonate and which percentage of that 5 grams is sodium chloride. So one thing he does is he takes the 5 gram sample and he adds it to concentrated hydrochloric acid. And what he's going to do is, because you're told this is concentrated hydrochloric acid, that's them trying to tell you that you're not going to run out of hydrochloric acid. That's going to be your excess reactant. So what's going to limit the reaction from taking place is the amount of either sodium chloride or the sodium carbonate, whatever is reacting with the HCl. And so you're told that he reacts the 5 gram mixture of sodium chloride and sodium carbonate with hydrochloric acid solution, and he measures the amount of CO2 produced. So CO2 has to be produced, okay? And so, again, he takes the 5 gram sample of the mixture that contains both the sodium carbonate and the sodium chloride. He adds it to hydrochloric acid, CO2 gas is produced, and from the amount of CO2 gas produced, you're trying to figure out the percent by mass of that 5 gram mixture. All right? So that's the idea. All right. So we're told the volume of CO2 gas produced, and notice that it's milliliters here, and it's at standard temperature and pressure. Remember, that's our clue that we can use 22.4 liters per mole when we're talking about a gas, and CO2 is in the gas state, right? Okay. So if we look at the overall reaction that's going on, we got to understand that sodium chloride doesn't react with HCl. Nothing happens, right? So it's got to be the sodium carbonate that's reacting with the HCl. And again, if CO2 is produced, our only source of carbon and oxygen from the two possible reactants, NaCl and Na2CO3, is the carbonate ion. So obviously the carbonate ion is where the CO2 gas is coming from. But if we look at the overall balanced equation and we think double replacement reaction, right? Remember, in this case, the sodium carbonate started out in the solid form, right? We added that in the solid form, and it was to an HCl aqueous solution. If we're thinking double replacement, we would end up with sodium chloride, right? The sodium would come in and replace the H plus, and you get sodium chloride. That would stay dissolved based on solubility rules. And then you would get H plus and CO3, you would get carbonic acid, okay? Well, if I look at this first equation I wrote here, I don't see CO2 anywhere. And we know CO2 is a product. So the question is, where did that come from? Well, let's try to go to the net ionic equation. So from the molecular equation here, what's going on? What was the net ionic equation? Well, we would keep sodium carbonate together because it's a solid. We would separate HCl because it's a strong acid, so H plus and Cl minus. This is aqueous sodium chloride, so that would dissolve or separate. And then carbonic acid is actually going to be written as H2O and CO2. So remember, if we refer to our predicting the products cheat sheet, remember if carbonic acid is produced in a double replacement reaction, you should really write it as water and CO2 gas in the net ionic equation. Okay, so that's where the CO2 is coming from. So yes, carbonic acid is produced, but it's not a very stable compound, and it pretty much immediately decomposes and forms water and CO2. So that's our source of the CO2. Okay, so if we go back to the equation, we'll see that we really only have one spectator ion. The chloride ion is a spectator because it's dissolved over here and it's dissolved over here. But notice this time sodium's not a spectator ion because it started out in the solid state on this side, so we didn't dissociate. So this, if we needed the net ionic equation, this would be it. And we do need to know, what's going to be the ratio of CO2 gas to sodium carbonate, which is our source of the CO2 gas, and it's a 1-to-1 ratio. So everything else not really necessary for this question, but we had to understand that if sodium chloride, if we go back up to the question, we had 5 grams of the mixture. Remember, this mixture had NaCl and sodium carbonate. The NaCl is not reacting with the hydrochloric acid. It's dissolving in the solution, but it's not reacting with the hydrochloric acid. So it's really just the sodium carbonate that's reacting, okay? So we don't care about the sodium chloride right now, okay? So if we want to visualize what's happening, right, we have an HCl mixture. We have excess H plus and Cl minus, but we draw that dissociated. We took the 5-gram solid sample, we threw it in that solution, and what will we see, okay? We would see bubbles form, and that would be the CO2 gas escaping from the solution. We call that evolving. Like if it forms a solid precipitate, we call that precipitating. If a gas forms in solution and bubbles out, we call that evolving. So just in case you see that terminology. So those bubbles are CO2 gas bubbles bubbling out of solution. And essentially what happened was, what did the student do in this lab? They captured the CO2 gas that was produced and they figured out its volume, okay? But if we kind of visualize what's going on here, we would also get sodium ions because all the sodium has dissolved in solution. And if we really think about what's going on here, you have chloride, but you have an extra amount of chloride than what you started with, because remember, in our 5-gram mixture, part of that was sodium chloride. So the sodium chloride dissolves. So you get sodium ions from the sodium carbonate reacting and dissolving, but you also get sodium ions because the sodium chloride that was in the 5-gram sample would also dissolve. So you get a bunch of sodium ions dissolved in solution. And you would also get more chloride than what you started with, right? So we had chloride in there because we had H plus and Cl minus. But then we would also get more chloride when the sodium chloride from the 5 grams mixture dissolves. Okay, so we would get sodium ions from the sodium carbonate dissolving and the sodium chloride dissolving, but we'd also get extra chloride ions as well. Okay. Notice how in our final solution here, we didn't write any carbonate ions dissolved, and that's because all of the carbonate is leaving the solution in the form of CO2. And I know all of the carbonate reacts because we know that HCl is our excess reactant. So what's limiting this reaction? When we run out of carbonate. So all the carbonate's gone. It's no longer in the solution, it's in the form of CO2 gas, all right? Okay. So it really just comes down to stoichiometry. Take what you're given and convert it to moles, right? We have our balanced equation. We were given the volume. Remember, we were given the volume in milliliters, but we would convert that to liters. So we had 0.8875 liters of CO2 produced, divided by molar volume, 22.4 liters per mole. And the reason why I can use this conversion to get moles of CO2 is because I was at STP. Our mole ratio of sodium carbonate to CO2 was 1-to-1. And then right here, this 106 0.01 grams. That's the molar mass of sodium carbonate. And the reason why I'm converting to grams of sodium carbonate is because I wanted the percent composition of the 5-gram mixture. So what I want you to notice is if I divide by 22.4 and then I multiply by the molar mass of sodium carbonate, that's going to give me grams of sodium carbonate that were in the 5-gram sample. So if I want to find the percent, I would take whatever this comes out to be. So that comes out to be, when you do the math, around 4.2. 4.2 grams of sodium carbonate were in the 5-gram mixture. And if you want percent, you would divide by the total. So 4.2 grams of sodium carbonate divided by the mass of the entire mixture, 5 grams, times 100. And that gives me the percent. So in that 5-gram sample mixture of sodium carbonate and sodium chloride, we found that 84% of that 5 grams is sodium carbonate, and that would mean the rest is the sodium chloride, all right? So that kind of answered our question. So again, if you go back and review, we had a white powdery substance, and we knew what was in it. We knew we had sodium chloride and sodium carbonate, but we didn't know how much of each thing we had. And so we wanted to figure out the percentage. So we took 5 grams of it, of that mixture, reacted with HCl, knowing that the HCl would only react with the sodium carbonate and not the sodium chloride. We figured out how much CO2 was produced. And then from that, we figured out how much sodium carbonate we had in the 5-gram mixture, and then we found the percent by mass. Okay? And so again, that's what we have here. Okay, so that's the percent by mass of the mixture. So if you do the math, that means 16% was sodium chloride. Okay, so our mixture of sodium carbonate and sodium chloride mixture was 84% sodium carbonate, 16% sodium chloride by mass. Okay, all right, so let's add a little extension to this problem. What if we were told our final volume of the resulting solution was 50 milliliters, and we want to know the molarity of sodium ions dissolved? So we have the volume in liters, 0.05 liters. We want the molarity. So we need to figure out how many moles of sodium are dissolved and divided by the volume, and we're told what that volume is, 50 milliliters. And that'll give us the molarity, right? So let's think about it. Let's go back up and look at the picture. So remember, our final solution right here has 50 milliliters volume and a bunch of sodium ions. But there were 2 sources of sodium, the sodium carbonate and the sodium chloride. So we have to figure out total moles of sodium dissolved and divided by the volume. But there's 2 sources of sodium, right? So we had the sodium chloride dissolving, but we also had the sodium carbonate dissolving. And notice when sodium chloride dissolves, we get 1 sodium ion for every 1 sodium chloride. But when sodium carbonate dissolves, we get 2 sodiums for every 1 sodium carbonate. So because we just figured out the percent by mass, remember, we added 5 grams of this mixture in it. And now we know of that mass, 84% is sodium carbonate and 16% is sodium chloride. So that means we have 4.2 grams of sodium carbonate dissolving, and we have 0.8 grams of sodium chloride. So all I did was 0.84 times 5. That gave me the mass of sodium carbonate that would be dissolving. And I did 0.16 times 5, and that would give me the mass of sodium chloride dissolving. So we need to figure out total moles of sodium. So to figure out the sodium that we get from the sodium carbonate, we would take the mass of sodium carbonate divided by the molar mass times 2/1. That would give us moles of sodium dissolved from the sodium carbonate. But don't forget, there's still more. So we had 0.8 grams of sodium chloride divided by the molar mass of sodium chloride, and that's a 1-to-1 ratio. That gives us moles of sodium from the sodium chloride. So if we add these up, that would be total moles. To get the molarity, we would divide by the volume. We were told 50 milliliters, so 0.05 liters. And we get the molarity of the sodium ions in the resulting solution. Okay? So hopefully that made sense to you. And just wanted to give another practice video. This is, another, the video before was a stoichiometry video. This is a stoichiometry video. There's a bunch of different ways we could ask stoichiometry questions, but it's really going to come down to, how well do I know my chemical reactions? and really, can I visualize what's going on, right? So I had this 5 gram sample of 2 different solid compounds, mixed all together, 1 sodium chloride, 1 sodium carbonate. And our goal was just to figure out what percentage of that mass belonged to the sodium carbonate and which percentage of that mass belonged to the sodium chloride. Okay. All right. So that's it for this review lesson. Hopefully you learned something. All right. Have a great day.